Hello, I'm Jonathan Aldrich, and today we're going to talk about scanning. So the first task of a compiler is called lexical analysis, which is also known as scanning. What we're going to do is divide the source code into a sequence of tokens. So if we have this program here that computes factorial, we're going to divide it into tokens like x and y and assignment and semicolon and while and do and all the other pieces that are part of this programming language. But really it's one word or symbol at a time that we're capturing. So the lexical analyzer is the first step in discovering the syntax of the program. In addition to producing a sequence of tokens, it's going to remove comments because we won't be using them later on in the compiler. They don't contribute. They're only for the person reading it. They don't contribute to the meaning of the program. We're going to save the text of identifiers, strings, and numbers so we know which number was a symbol, not just that it was any number. And we'll also tag tokens with line numbers so that we can give good error messages to the user. So for scanning, imagine that we're building an ad hoc or handwritten scanner for a calculator language. So we want to read the characters one at a time. We'll do some look ahead to see what the next character is. That'll help us decide what to do sometimes. So if we read one of the one-character tokens, like open parentheses, close parentheses, plus minus times divided by, then we'll just announce the token that corresponds to that one character. If it's a digit, we keep reading digits until we can't anymore, and then we'll announce that we found a number. If it's a letter, well, that's going to be the beginning of an identifier. So we keep reading letters and digits, and maybe underscores until we can't anymore, and then we'll announce that we found an identifier, or perhaps a keyword, which is usually just treated as a subset of the identifiers in our language. So what happens if we want to scan floating point numbers? Well, if it's a digit, then we'll keep reading until we find a non-digit. If that is not a period or a dot, then we announce an integer. Otherwise, if we have a dot, then we keep looking for a real number. And if the character after the dot is not a digit, we announce an integer. And we reuse the dot in the look ahead, right? So maybe our language has dot in some other context. And so 100 dot might be the integer 100 followed by a dot and then something else, right? So it depends on our definition. But with this approach, you can see how we can sort of code up a scanner that figures out what the tokens are. We can look at this, the structure of this scanner, essentially as a state machine, right? So here's a pictorial representation. If you look at the textbook, you can see a bigger version of this. But essentially, we're going to start at the very beginning. We have some self loops where we just ignore spaces and tabs and new lines. We ignore white space. And then we do the things that I just described, right? So there's some text at the beginning for recognizing comments. If we see a slash, then we go into a little state machine for finding comments. If we see a left paren or a right paren, we announce left paren token, right paren token, et cetera, for the other symbols. And if we see a dot, then we get into, if we see a digit, then we get into exactly the description that I just described to you, right? Where we're finding digits, and similarly for letters, that allows us to find an identifier, right? So with this little state machine, we can identify all of our different tokens one at a time. So scanning can be described with this little state machine, which is also known as a deterministic finite automaton. It's deterministic because no matter what symbol comes in, we know where to go. It's a finite automaton because it has a finite number of states, which we transition between as we read characters. So there are tools like lex and scangen and so on that build these things automatically from a set of regular expressions. So in particular, they construct a machine that accepts a language of identifiers or integer constants or real constants or comments or symbols, et cetera, right? And so basically what we're going to do is we're going to run the machine over. We're going to run the machine once, and we'll get a token. And then we'll run the machine again, starting from where we stopped after we got that last token. One nearly universal rule present in basically all languages is that we're always going to take the longest possible token from the input, right? So if we see the input foobar, then we're going to report the token foobar and never just, the identifier f for foo or foob or something, right? More to the point, 3.14159 is a real consonant. We're not going to recognize it as a 3 and then a dot and then 14159, right? So we pick the longest token we possibly can given the definition of the scanner. So we say that regular expressions, like the ones we described in the last lecture, generate a regular language, and DFAs recognize that. So DFA is what goes from the input text to the token. Now we can implement scanners in three different ways generally. One is ad hoc, right? That just means we program it up as in the intuitive way that I described earlier. There's also a semi-mechanical pure DFA. So this is code that you write, but you write it in a particular style, right? Usually with nested case studies, you use nested case statements to determine, based on the code that just came in, where do you go next? You can also have a table-driven DFA, where you have a table off on the side that tells you what to do next. So the ad hoc scanners tend to be the fastest and most compact code. And they do that because you can do special purpose things, right? You can recognize, oh, there's this particular common pattern in this language, and so we'll write the scanner in a way that captures that efficiently. However, if you have an automatically generated scanner and you use a good approach to that, you can come very close, right? So people who are, fully industrial strength implementations might use ad hoc scanners, but for a lot of languages, it's just as good to use an automatically generated scanner. So writing a pure DFA as a set of nested case statements, it turns out, is a surprisingly useful programming technique. You can also use tools like Perl, awk, or sed. For details, you look in the textbook. Example 2.16 has some examples of this. You can also use a table-driven DFA. That's what Lex and ScanGen produce. Lex produces it directly in the form of C code. ScanGen produces numeric tables and a separate driver that does this. And there's also some figures in the textbook that you can use to find this. As far as scanning, there are some implementation challenges. Notice that the rule about the longest possible tokens means that you return from recognizing a token only when the next character can't be used to continue the current token, right? So you have to program up the recognizer in a way that accounts for this. And whatever that next character is, you're basically peeking at it, but you're not using it. You want to save it for the next token. In some cases, you might need to peek at more than one character of lookahead to know whether to proceed or not. So for example, in Pascal, when you have a 3 and you see a dot, do you proceed with recognizing a floating point number like 3.14, or do you stop because you're going to get a range, 3.5? So you actually need to look a couple of characters ahead in Pascal to figure out what to do. There are also messier languages where you actually can't get by with any fixed number of look-ahead. No fixed number of symbols will tell you. So for example, in Fortran, this is kind of an astonishing example. You can have do 5I equals 1, 25. That is a loop. You can also have do 5I equals 1.25. That is an assignment to the variable do 5I. Okay, so loop Fortran has this weird syntax where you can put spaces in the middle of identifiers, and it doesn't break up the identifier. So maybe a lesson not to design your language in the particular way Fortran was designed, right? But just to let you know, there are definitely some complications when you are implementing these things. In this case, what we do basically to deal with these kinds of situations is remember that we were in a potentially final state and save information so that we can get back to it, right? If we get stuck looking for a loop and we want to go back and find an assignment, we can get back to it and continue where we were before. All right, let's do an in-class exercise. In a language with a while keyword, let's say we have the input while_away. What should the scanner return? Should it be a while keyword token, or should it be an identifier token while away? Okay, in summary, when we do lexical analysis, we use regular expressions to define tokens. Regular expressions are defined using concatenation, alternation, and repetition. A scanner will use a DFA to recognize tokens. This DFA might be machine generated, but we can also do it by hand. In the next lesson, we'll see how to construct DFAs directly from regular expressions. Finally, context-free grammars, or CFGs, define higher-level structure. We have to structure the CFGs in the right way to avoid ambiguity. And in the lesson after next, we'll look at how to parse a CFG. See you then.